All right, hello again, everyone. So again, I'm still Miles Norsley. The talk that I have today is redox states and axons and dendrites. So starting off, when we're thinking about oxidation, we typically think about oxidation as kind of like being this villain. So we've been aware of oxidation for literally thousands of years. Typically think of like oxidation, you can think of rust. So you've been to Chicago before, you probably recognize these lion statues here. So they've gone through an oxidative state. And it wasn't always obvious that this process of oxidation reduction was actually happening within our cells, within biology as well. And when we did figure out that it actually was playing a role, we kind of thought of it as being almost universally this evil, terrible thing. So we have an image of Denham Harmon here. So he's kind of called the father of oxidation, the concept of aging. So we know that everything ages, we know everything gets older and dies. The question is, okay, what causes it? And he kind of came up with this theory that oxidation is the main driver of aging for all different organisms. So we kind of see oxidation or redox within biology as kind of being this Pandora's box of evil causing all these different issues within the body. And that is to a degree very true. So we have oxidative damage of DNA leading to cancer, and there's all kinds of different disease processes that are shown out have increased oxidation within the cells as well. However, redox in general within biology is more complicated than that, and is actually can be part of normal cellular function. So one example we have for that is airway remodeling and fibroblast differentiation. So making sure we have the proper structure of their lungs. If you look at nitric oxide, so we have a ton of research about that as far as going for vascular tone, heart health, and things like that. So again, natural part of our physiology. And more specifically for what I'm looking at, we also have functions within the brain as well. So we have regulation for synaptic plasticity, long-term potentiation, neurogenesis, and even more specifically, looking at cytoskeletal control within individual neurons. Now, obviously, cytoskeleton is important for any kind of cell in our body, but neurons have certain requirements for their overall brain function that are highly dependent on the cytoskeleton. So here we have the cell body, the soma, and then we have the dendrites, so we think of information going in, and then we have the yellow arrows for axon, we think of information going out. So we need to have this specific, very stretched out architecture of the neurons so it can make the proper connections within the brain to have proper brain function. So the question then comes, okay, well, how do we actually do that? And there are various mechanisms by which we have this very specific architecture and these networks form within the neurons. One of those guides is semaphorin 3A. So there's 20-member family of semaphorins. 3A is one of the secreted family of semaphorins, binds to plexus neuropilins that are found within the membranes of neurons itself, and it functions as one of these extracellular growth cues. What makes this interesting is that it has two different functions for both the axons and the dendrites. So for axons, it functions as a negative growth cue. It was originally called collapsing because it causes a catastrophic collapse of the axon growth cue. So it happens within minutes. It also causes suppression of cyclic AMP, activation of MyCall, which causes that collapsing. And that collapsing, that function of MyCall is done via active oxidation. And MyCall itself also generates hydrogen peroxide. So we can think of the axon, this function downstream of semaphorin 3 as being highly oxidative. Then for dendrites, of course, we have a slightly milder but completely opposite effect as well. So it functions as a positive growth cue. We have that cyclic increases cyclic GMP, which kind of acts counter to cyclic AMP. And it also requires a reduced environment as well. So for the cyclic cyclase to produce a cyclic GMP has to be in a reduced state for that to actually function. So given this effect, we kind of ask the question, okay, do axons actually have more oxidized state just left on their own compared to dendrites? So looking at that, we find that in fact there isn't actually a difference between that. So looking at data in vitro 2, 4, and 7. So we get the y-axis, so as it gets higher up, the axons are more reduced compared to the dendrites of the same cell, and the inverse as you go further down. So we do see that they actually overall do maintain about the same level of redox state. And this is specifically looking at the glutathione redox state within those cells, glutathione being basically the biggest contributor to maintaining the redox state within the cells. So you see that there is a significant spread that we have between the two of those. So once I had information, I also did a Scholl analysis to see whether or not for those neurons that had more oxidized axons had a different level of, or perhaps more mature than those axons that were more reduced than their dendrites within that given cell. So look at the complexity. So starting off with 10 micrometers, moving out 20 every looking at those two different populations. Again, not seeing a significant difference between those two populations where the axons are more oxidized versus more reduced. Then also using something called also looking at theoretic length in general, didn't see a difference. And finally, looking at the branching index, which is just a more sensitive means of looking at the show analysis, we didn't actually see a significant difference between those two. So not super exciting, but it does turn out that there isn't actually a big difference between those two. However, what that does answer is whether or not there is equal sensitivity between redox environment with or without the semaphorin. So again, when we're thinking about the neurons, we think about them being highly polarized, and the substrate cues are influencing the polarity and guiding axons as well. So first thing we did is looking at the actual hippocampal axon length and looking whether or not, once they're actually a 24-hour bath with either glutathione, which is reducing, hydrogen peroxide, which is obviously oxidizing, with or without that semaphorin, and seeing whether or not we see a difference overall axon length is altered by there. So we can see that there is actually a significant difference between both the control for the hydrogen peroxide, and that's also been shown in other people's work as well. So we see a reduction in the axon length, and then we also see a reduction in the axon length for the semaphorin 3A. So both of those were what we expected. However, looking at the hydrogen peroxide along with sema, we actually see that there isn't a significant difference. So this reduction in axon length is actually abolished when you put those two together, which was actually kind of surprising. We would expect it to be kind of like an additive or at least the same as hydrogen peroxide and semaphorin. So there does appear to be an interaction between the semaphorin effect along with redox states as well. So we also looked at the hippocampal dendrite length. So we expect it to be slightly more of a mild change as well. And again, looking at the control, so we see a significant difference where we've had both the glutathione and the semaphorin 3A. So we actually do see a slight increase actually when you have those two as well. Also, interestingly enough, glutathione just by itself was actually apparently slightly stronger increased dendritic length than semaphorin itself, which was also kind of surprising, but does kind of match the hypothesis that you have this more reducing state for that dendrites actually have that increased growth overall. Then finally also looked at the amount of dendrites that are actually produced for each of the individual hippocampal neurons. But for that, we didn't see any significant difference because we also think the cyclic AMP and GMP is kind of being determiners for the generation of both axons and dendrites. But we didn't see a difference for that as well. So moving on, so what so far I've just been talking about the actual like a bath application, but we also want to look at more selective or local application of these various semaphorin and our reducing and oxidizing reagents as well. So to do that, I've been using microfluidic devices. So you can see the central channel. I'm able to chemically isolate the cell soma from both the dendrites and the axons, and then expose just the axons and dendrites to these different conditions and see how that actually alters their actual movement and their activity as well. So we'll be doing, or have been doing that in conjunction with spatial light interference microscopy, or SLIM. So it's kind of hard to see, but you can see there's just a slight bit of movement, the filopodia. So this is the tip of an axon of a de in vitro 4 rat hippocampal neuron. So this, again, we've been talking about label and stain-free imaging. This is one of those as well. It's topographic actually comparable to atomic force accuracy, but it's about 1,000 times faster as well. So we get very detailed dry mass change information as I'm applying all the different conditions to those neurons as well. So I'll be continuing to do that in those same conditions that you saw before for both the bath application, and looking at those rates of change, if there are any, and seeing how they compare to just a like 24 or 70-hour bath application as well. I'd like to thank all my committee members, the lab members, all the collaborators as well, and of course, all my cats and my wife. And if anyone has any questions, please ask at this time.